Hey guys, welcome back. Okay, so this is the second video of the series. Once again, still Cal 2. I'll be covering two major topics, which is summation notation and area approximation using the limit process. Now, unfortunately, in this section, I have to go a little bit more theoretical. It's extremely important that you understand the theory and the notations behind it. So bear with me. Hopefully, you'll learn something and enjoy. Okay, so let's take a look at the summation formulas that are required for this section. Now, the reason why these are so important is because we're going to have to use these to be able to find the area underneath the curve using the limit process. So these are the four major ones we'll be using. Hopefully you looked at summation formulas before in the past, pre-cal, maybe even cal 1, but here we go. This is what they are. So it's the sum as I goes from 1 to n of a constant. So all we have to do is multiply the constant by the upper limit, and we know what the sum is automatically. The second one is we try to transform it with I. So therefore I is simply n times n plus 1 over 2. The next one, I squared. So the sum of I squared as I goes from 1 to n is simply n times n plus 1 times 2n plus 1 over 6. And finally the last one is I cubed, which is n squared times n plus 1 all squared divided by 4. Now, we're going to use these and we're going to try to do a couple of examples and see if you can understand the concept. So, example number 1. We have find the sum as k goes from 1 to 6 of k times k minus 2. Now, whether it's k, whether it's I, it's interchangeable. But in this particular case, what I'm going to have to do is going to have to distribute. Simplify. And I get k squared minus 2k as k goes from 1 to 6. Now I notice there's a k squared and I notice there's a formula for I squared. And I also see there's a 2k. Well, 2 is a constant. So I can rewrite this. And therefore I get 2 times k. I, k, same idea. I can take out the 2 because it's a constant value. And therefore now I have the sum of k squared and the sum of k, as k goes from 1 to 6. So, it resembles the formula number 3, which is n times n plus 1 times 2n plus 1 over 6, and of course the other one, which is I, which is n times n plus 1 over 2. So, I look here and simply replace. I look there, and once again, it's going to be 2 times n plus 1 over 2. Now, where does the n come from? Well, we can look at the upper limit, which in this case is 6, but that's not really how we find n, the number of terms. We really take the upper limit, 6, we subtract it from the lower limit, 1, so 6 minus 1 is 5, and then we add a value. So if you want to try that, you can count on your fingers and you'll get, 6 values for n. So all we simply do now is replace n with 6, evaluate, subtract, and there's the value. So 49 is the sum of 6 terms of k squared minus 2k. Okay, so let's take a look at the second example. We have the sum as k goes from 1 to 10. However, we notice that there's two variables in this one. We have a k and we have n squared. Now what we really need to focus on is the k. So what I can do is I can rewrite this equation and simply factor out the n squared, which becomes 1 over n squared. I can simplify my life even more by removing the 4 in front of the k, because once again, we're going to go back to those 4 formulas where we have a single value, which is in this case k. So we factor out a 4, and I'm left with k plus 3/4. So we have k plus a constant, and this can be rewritten as the sum of k as k goes from 1 to 10 plus 3/4 as k goes from 1 to 10. Now we know what the formula for k is, and we've seen that previously, which is n times n plus 1 over 2, and plus 30 over 4. Now where does the 30 over 4 come from? Well, that's quite simple. Remember, n represents the number of terms. 10 minus 1 is 9, 9 plus 1 is 10, therefore 3 times 10 is 30, 30 over 4. We simplify this expression, and we get 2 times n plus 1 over n, plus 30 over n squared. And all we have to do now is replace n with the value with the number of terms in this problem. And that is 10. So 2 times 10 plus 1 over 10 plus 30 over 10 squared. Simplify, and there we go, 5 over 2. Okay, so now we're going to take a look at the area of a plane region. So in other words, the area underneath the curve. But we're going to do this through approximation. And then eventually I'm going to bring what we brought in earlier, which was the summation notation formulas, and use those to give us a better approximation of the area underneath the curve. So let's pretend we have this curve y is equal to x squared plus 5, and we have the value of a, which is 1, and the value of b, which is 3. And of course in the middle, well, we have the value of 2. There are two methods for approximating area. We have the left bound, which is called the lower sum, which is underneath the curve, and we have a right bound, which is called the upper sum, which is above the curve. So what does this mean? Above the curve, below the curve? Well, I'll show you, because we're going to have to create rectangles to be able to figure out and to approximate the area underneath the curve. Okay, so we're going to take a look at this example, y is equal to x squared plus 5, and we're going to try to approximate the area between 1 and 3. So, what is left boundary or lower sum? We need to draw rectangles, and we want to draw the rectangles in a way such that the left side of the rectangle touches the curve. Now, how many rectangles are we going to draw? Well, it depends. For this particular case, we'll decide the number, and I chose n to be 4. So the number of rectangles that I want underneath this curve is going to be 4. Now that number can change. It can be 8, 10, 15, 12, doesn't matter. Okay, most problems in the book, they'll actually tell you the number of rectangles that they want you to use to be able to approximate area. But for now, we're just trying to understand the difference between the left boundary or lower sum and upper sum. So let's take a look. This specific formula is used to find the width of the rectangle, where n represents the number of subintervals or the number of rectangles that I want to use. Now the b is my upper bound, the a is my lower bound, and n of course is the number of rectangles I'm going to use, and in this particular case, like I said before, it's going to be 4. So our upper bound is 3. 3 minus 1 divided by 4 gives me a half. So what is a half? Well, a half is actually the width of the rectangle. So if a half is the width of the rectangle and I'm starting at 1, it's going to be from 1 to 1.5, 1.5 to 2, 2 to 2.5, and finally 2.5 to 3. There are my 4 rectangles. And what I want you to notice is that the left side of the rectangle is touching the curve. Each one of those rectangles is below the curve. So there's a bit of the curve missing, there's a bit of the area missing. However, it still gives me a pretty good approximation of the area underneath the curve. Now, of course, the more subintervals or rectangles I use, the better the approximation. Now, if I find the area of one rectangle, and find the area of the second rectangle, and find the area of the third and fourth, and I add up those areas, that would give me a pretty good approximation of the area underneath the curve. So all I need to do, I know the width, all I need now is the height. So we know that height is going to be f of 1, the next one will be 1.5, the next one will be f of 2, and finally the last one will be f of 2.5. So to be able to approximate the area, it's quite simple. We're going to find the area of each of these rectangles. So how do we find the area? Well, the height times the width, the height times the width, and so on and so on. And what does f of 1 mean? Well, that's quite simple. I simply replace 1 into my original function, which is y is equal to x squared plus 5. So I end up with 6 times 0.5 plus 7.25 times 0.5 plus 9 times 0.5 plus 11.25 times 0.5. And when I simplify all of this, I end up with an area of approximately 16.75. Now this is simply an approximation. It is not the exact area. We're going to have to learn techniques later on to find the exact. But this is a pretty good, a decent approximation of the area underneath the curve using lower sums. Okay, so we're going to use the same example, y is equal to x squared plus 5, but this way we're going to look at the upper sum or the right boundary. Now we're going to draw rectangles like we did with the previous example, except that this time we want the right end of the rectangle to touch the curve. And once again, we're going to decide the number of rectangles, and we're going to choose 4 to be the number of rectangles. Now, once again, the upper limit minus the lower limit, 3 minus 1, divided by the number of rectangles, in this case 4, equals a half. What is a half? The width of the rectangle. So from 1 to 1.5, from 1.5 to 2, 2 to 2.5, and finally 2.5 to 3. Now, we know what the width of the rectangle is. All we need now is the height. And in this case, we're going to evaluate f of 1.5, f of 2, f of 2.5, and finally f of 3. So the numbers are a little bit different from the previous example we did because now it's the upper sum. It's larger than the curve versus the lower sum, which was lower than the curve. Kind of makes sense. So we're going to approximate the area. We're going to evaluate the height times the width of every one of these 4 rectangles. Simplify, add, and we end up with an area of 20.75. The previous example gave me an area approximation of 16.75. Well, that was below the actual area. This one is above the actual area. So that means that the real answer, the real area underneath the curve, should lie anywhere between 16.75 and in this case 20.75. Okay, so now we're going to take a look at the limit of lower and upper sums. Now unfortunately, I'm going to have to be a little bit more theoretical here. So we have this formula which says the limit of the sequence as n approaches infinity is equal to the summation of f of m sub I times delta x. Okay, so let me just simplify this a little bit. F of mi times delta x. I want you to think of delta x as the width of the rectangle, and I want you to think of f of mi as the height of the rectangle. But what I want you to understand is that the small mi represents the left bound or the lower sum versus the capital Mi, which will represent the right bound or the upper sum. So if I'm using the small letter mi, that means that the rectangle will touch on the left side. If I'm using capital Mi, then that means that the rectangle would touch on the right side of the curve. So little mi below the curve, capital Mi above the curve. And of course, when we take the limit of the sequence as n approaches infinity, I end up with the area underneath the curve. Now that's not that important, so don't worry about it too much, but what I really care about, what really matters, is this notation of the sum of f of small mi versus the sum of f of capital Mi times delta x. And don't forget, of course, where delta x is equal to the upper bound minus the lower bound divided by the number of rectangles that we use. So this is the intro to how we're going to start finding or approximating the area underneath the curve using the limit process. Okay, so we're going to take a look at the definition of the area of a region in the plane. Now, here's where my students start to get a little bit confused because we start changing variables on them and they don't understand, but why did we use m and now we're using a different variable? You just need to be patient. It's all going to make sense as we get through this. So the area underneath the curve is the sum of f of ci times delta x. Okay, so ci, well, little mi represented the value to the left, or the left side of the rectangle. Capital Mi was the right side of the rectangle. Well, Ci is simply the middle number, the number that lies in the middle of the upper and lower sum. So depending on the number of rectangles that are being used, the more and more rectangles that are being introduced, or the more and more rectangles that I'm using to approximate the area, well, then eventually m sub I and capital M sub I and C sub I all become the same thing. They all become one. So that's why the actual formula or the definition uses C sub I. Here's where it starts to get even more confusing. Well, what do you mean C sub I lies between x sub I minus 1 and x sub I? I don't know why, but it seems that mathematicians really like to confuse people. Makes us feel a little bit smarter. So once again, the change of x still represents the upper bound minus the lower bound divided by n. And I think this picture will really make sense. So if you take some time to take a look at it, what's going on is this. I want you to think of the x sub I minus 1 as the left side or the lower sum. And I want you to take a look at the x sub I as the upper sum. And well, there's a value that lies in between those two, which we call c sub I. So f of c sub I would be the height, and of course the width is still delta x. So the height times the width gives you the area of the rectangle. Once again, don't focus too much on this notation. It's extremely important that I explain it to you, but yet I don't want you to overexert yourself or go crazy trying to understand it too much. It's pretty basic, pretty simple. Instead of looking at the left or looking at the right, we simply take a number that is in between and we evaluate that and find the area of that rectangle. Okay, so this is a good way to sum up what we just spoke about. The limit of the upper sum is equal to the limit of the lower sum as n approaches infinity. So if we increase the number of rectangles, then eventually the limit of the upper will equal the limit of the lower. Now we can choose an arbitrary x value in that subinterval. Now usually we either choose the minimum or the maximum value. So in other words, we'll choose either small m sub I or capital M sub I to be able to find the limit or to approximate the area underneath the curve using the limit process. However, what we need to understand is that eventually, whether it's the lower bound or the upper bound, that value in the middle is all going to be the same thing. So take a look at this picture and hopefully it'll make sense now. I drew 3 rectangles, and as you can see, they are the lower bound rectangles because they are below the curve, and we have that little m sub I which happens to touch the curve. And c sub I lies right in the middle of the subinterval. Now, if I draw the rectangles where the right side touches the curve, now that changes a little bit because now we have capital M sub I. So little m sub I represents the lower bound, capital M sub I represents the upper bound, and finally c sub I is simply a number in between that subinterval. Hopefully that clarifies quite a bit. Alright, so we're going to take a look at some general notation. Now, A is my lower bound, and we know that B is my upper bound. And how do I get my subintervals? Well, by simply adding the width of the rectangles, and that's where that 1 times delta x and 2 times delta x comes in. Not that important. Don't worry about that too much. What is really important here is the left endpoints of the rectangle, which we also know as the lower sum. There's a specific formula for little m sub I, which is a plus I minus 1 times delta x. Now I'm introducing the I value here, or the I variable here. So I want you to think back at those 4 that I taught you for summation notation. So now we're going to start using the summation notation formulas to be able to find the area underneath the curve using the limit process. For the right endpoints, which is the right endpoints of the rectangle, known as the upper sum, is capital Mi, and that formula is a plus I times delta x. Now the second formula for the right endpoints, or the upper sum, is a lot easier to work with than the left endpoints, or the lower sum. So you'll see that a lot of examples, many times students will use the upper sum formula, the capital M sub I, versus the little m sub I. So we're going to put all of this together with the area, the definition of the area, using the summation notation formulas of f of c sub I times delta x, and of course, once again, okay, where c sub I lies somewhere within that subinterval, and the change of x, the width of the rectangle, will simply be b minus a over n. So those 2 formulas, little m sub I and capital M sub I, write them down. Extremely important because that's what we're going to need to use. Okay, let's go through an entire example using the limit process and using the idea of limits, using the idea of the summation formulas, and of course understanding the left and right sums. So we have this function y is equal to x cubed, and we're trying to find the area underneath the curve between 0 and 1. So my lower bound is 0, my upper bound is 1. Now, first I find my change in x, which is the width of the rectangle. And in this case, I'm not saying the number of rectangles. So I'm going to leave n as n I will not change that value. So 1 minus 0 over n is simply 1 over n. And 1 over n will represent the width of the rectangle. I chose to go with the upper sum because it is a much easier formula to work with. So capital MI is equal to a plus I times delta x. Now I already have my delta x, it's 1 over n. So I can simply replace a with 0 because it's my lower bound, and I know that my delta x is 1 over n, so I simply get I over n. Alright, now what do we do with this? So really, I over n really is my CI. It's that middle number in my subinterval. So what do we do with this? Well, we simply evaluate f of CI. So I'm going to take this I over n and I'm going to replace it into my function y is equal to x cubed to evaluate. So it's 1 over n cubed times delta x, and delta x we found it to be 1 over n. So now we have to simplify this. We're going to have to use a little bit of algebra, and this is what we obtain. The sum as I goes from 1 to n of I cubed over n to the power of 4. Now, because we know the formulas for I, going back to the summation notation formulas that I gave you previously, we're going to keep I cubed, but we're going to factor out 1 over n to the 4th as I goes from 1 to n. So going back, I cubed we said was n squared times n plus 1 all squared over 4. So simply put, I get n squared times n plus 1 all squared over 4 times 1 over n to the 4th. We're going to distribute and simplify. Simplify further, and I end up with 1/4 plus 1 over 2n plus 1 over 4 n squared. Now when we evaluate the limit as n approaches infinity, going back to what you learned in Cal 1, 1 over 2 to the n, as n gets larger and larger and larger, that expression or that part gets smaller and smaller and smaller, which means it equals 0. And the same thing for 1 over 4 to the n squared. As n gets larger and larger and larger, 1 over 4n squared approaches 0. So what do we end up with? Simply a quarter. So the area underneath the curve between 0 and 1 is a quarter. Okay, so let's take a look at another example. This one is finding the area underneath the curve using the limit process. Okay, so using what we used previously, we have this function y is equal to 4 minus x squared, and we're looking within the interval negative 2 and 2. In this particular case, they didn't give me the number of rectangles to use. So I have to use the number of rectangles n to be simply n. So let's do this in steps because it makes it a little bit easier for students to follow. And if you use these steps, you'll see that going through the limit process is much, much easier. So step 1, finding the width of the rectangle. So we have b minus a over n. So it's 2 minus negative 2 over n. Since we don't know the number of rectangles, we simply leave n as n, and we end up with 4 over n. So there's my delta x. Step 2, decide upper or lower bound. So unless the problem specifically tells you which one to use, I always like to use the upper bound. It's a much easier formula to work with, and as you can see, it's simply m sub I, in this case capital M sub I, is equal to a plus I times delta x. We already found our delta x to be 4 over n. We know we have to multiply it by I, and I have my lower bound, which is negative 2. Simplify, and I get negative 2 plus 4i over n, which is really c sub I. Once again, going back to what I said previously, little m sub I, big M sub I, or c sub I. As the number of rectangles increase, eventually those three values will end up being the same. That's why, as n approaches infinity, it doesn't really matter. They all mean the same thing. Step 3. Evaluate f of c sub I. So now we're trying to find the height of the curve. But because we don't have the number of rectangles, we're just going to use the formula in general. So we're going to simply do 4 minus x squared, whereby x squared is simply negative 2 plus 4i to the n. Simplify, a little bit of algebra, and we end up with 16i over n minus 16i squared over n squared. That is the height of the rectangle. The delta x is the width of the rectangle. So now we have to add up all these rectangles together. So we simply evaluate the limit. So the limit as n approaches infinity is the sum as I goes from 1 to n of 16I over n minus 16I squared over n squared times delta x, which is 4 over n. Bit of magic, bit of practice. We simplify. We're trying to keep our i's together because we have the summation formulas regarding I. We simplify further. We break it up. And now, because the sum of I is n times n plus 1 over 2, and the sum of I squared is n times n plus 1 times 2n plus 1 over 6, but because it's over n multiplied by 1 over n, we simplify further, common denominator, all that stuff, and then we finally evaluate our limit as n approaches infinity. So we end up with 32 over 3, which is 10.67. What is 10.67? The area underneath the curve of y is equal to 4 minus x squared between negative 2 and 2. That is the actual area using the limit process. Now this is a pretty long process, but eventually I will teach you techniques so that we can find the area way quicker than the way we're doing it. But every final exam, no matter which Cal 2 course you're taking, no matter what college you're going to, they will always ask a limit process question. Okay, so we'll go through a couple of examples. These examples are a little bit different. So we're going to start off with just simply working with the summation formulas I gave you previously. So use the properties of summation to evaluate the following sum. So the sum is I minus 1 all squared as I goes from 1 to 20. Now, the only thing we can do is work with I. So what I'm going to do is simply distribute or expand. So I minus 1 all squared is simply I squared minus 2I plus 1. Because there's addition and subtractions, I can actually break this down. And I get I squared minus 2 times I plus 1. Now remember that all of these go from I equals 1 to 20. How many terms are there? Well, once again, 20 minus 1 is 19. Add 1, there's 20 terms. According to the formulas we learned previously, we know that I squared is n times n plus 1 times 2n plus 1 over 6. We know that I is n times n plus 1 over 2. And we know that c, a constant, is simply c times the number of terms, which in this case is 20. So when I replace n with 20, I end up with 20 times 21 plus 41 over 6 minus 2 times 21 times 20 over 2 plus 1 times 20. Final answer is 2470 or 2470. That is the sum of the first 20 terms of I minus 1 all squared. Okay, so this is how we use the properties. Now, in reality, what are we learning, or why are we learning to do this? For the limit process. That's really what we're getting into. To be able to find the sum, to approximate the area, or actually to find the area under the curve using the limit process. Okay, so the next example is approximate the area of f of x is equal to 9 minus x between the interval 2 to 4 using 6 rectangles. Now we call this an approximation because we're telling you to only use 6 rectangles. Now, if we did not give you the number of rectangles and we still use the limit process, then we would be able to find the exact area. But right now we're approximating the area because of the number of rectangles used. Of course, the more rectangles we use, the better the approximation would be. So, step number 1, as I showed you previously, we're finding the width of the rectangle. How do we find the width? Well, b minus a over n. Now we know that n is equal to 6 rectangles, so 4 minus 2 over 6 equals 1/3. So the width of the rectangle is 1/3. Now, I gave this example, I changed it up a little bit, and instead of doing the right bound, I chose the left bound, so little m sub I. Just to change it up a little bit so you can see how things work. So now we have this formula, a plus I minus 1 times delta x. We know what delta x is, which is 1/3. We know that a is the lower bound, which is 2. We simply multiply and simplify. And we know that this really works out to be c sub I. So whether it's little m sub I or capital M sub I, this all equals c sub I. we need to figure out what c sub I is. So that means that we're going to take this value and plug it into my function. 9 minus x, and x in this case is 5 plus I over 3. Common denominator, simplify, and we end up with 22 minus I over 3. So I have the height of the rectangle. I have the width of the rectangle. Now I need to add up all those rectangles. But more specifically, it's not from 1 to n, it's from 1 to 6 because I'm using 6 rectangles. We set up the equation, we simplify, we expand, we break it up, and we end up with 22 over 9 from, as I goes from 1 to 6, minus 1 over 9 times I. Once again, the summation of I, we've seen this formula before. We know that it's 22 times n over 9 minus n times n plus 1 over 2. Well, 2 times 1/9 is 18. What is n in this case? Well, 6 minus 1 is 5, 5 plus 1 is 6, so there's 6 terms. N is equal to 6. We simply replace n with 6, subtract, evaluate, and we get 12.33. So the approximate area underneath the curve between the values 2 and 4 of this particular function 9 minus x using 6 rectangles is 12.33. Okay, so we're going to take a look at another example, but this one's a little bit different than what we've learned before. This one, instead of finding the area with respect to the x-axis, we're going to find the area with respect to the y-axis. So the function changes a little bit. Instead of saying, g of x or f of x, now it's g of y. So g of y is equal to 1/2 y between 2 and 4. So the process is very, very similar. It's just a notation that changes a little bit. So let's take a look. Instead of the change in x, meaning the width of the rectangle on the x-axis, we're simply doing the width of the rectangle, but with respect to the y-axis. It's still the upper bound minus the lower bound divided by the total number of rectangles being used. Now, we're not given the number of rectangles, so we're going to use n. So in this particular case, we're not going to approximate the area. We're actually going to find the area underneath this curve. So in this particular case, I decided to use the upper bound. Okay, it's a lot easier to work with. It's much easier to work with. So it's a plus I times delta x, and I end up with 2 plus 2i over n, and we know that that is equal to c of I, or c sub I. But instead of evaluating f of c sub I, in this particular case, we're going to use g of c sub I because that's the function that I'm working with. We replace and evaluate, and now we simply use the limit process formula, which is the sum as I goes from 1 to n, not of f of c sub I, but of g of c sub I times delta y, not delta x. So we replace g of c sub I is simply 1 plus I over n, delta y is 2 over n, and now all that is required is a little bit of algebra. We simplify, we factor out what we can factor out. Remember that I'm looking to isolate the values of I because of the summation formulas that we learned previously. I broke it down to 1 plus 1 over n times the sum of I. We know what the sum of I is equal to, which is n times n plus 1 over 2. Multiply, simplify further, and now I have 2 plus n plus 1 over n as n approaches infinity. We're not done yet, we're very close. We're going to simplify this a little bit further, and we're going to end up with 2 plus 1 plus 1 over n. Now once again, we're evaluating the limit as n approaches infinity. We have 1 over n, so as n gets larger and larger and larger, 1 over n approaches 0. So what are we left with? 2 plus 1 plus 0. And 2 plus 1 plus 0 is simply equal to 3. So the actual area underneath the curve of g of y is equal to 1/2 y between 2 and 4 is equal to 3. And this is what the graph looks like. Hopefully this clarifies quite a bit. Okay, so finally, the last slide. Practice, practice, practice. Calculus is all about practice. The more practice you do, the better you'll get it, the better you'll understand, and the easier you will find Cal 2 to be. The next topic that I'm going to be focusing on, or the next video I'm hoping to upload, is going to be a Riemann sum. So hopefully you're enjoying this, and good luck.